Okay, this video is to help you with the calculation for the heats of reaction. Now, there's three parts to this lab experiment. The first part is you're going to determine the heat of reaction of aqueous sodium hydroxide and hydrochloric acid. So you're going to be mixing 100 mils of sodium hydroxide aqueous with 100 mils of hydrochloric acid. In a calorimeter. So the first thing that you need to do is take the temperature of both the sodium hydroxide and the hydrochloric acid. Now hopefully they're at the same temperature, but sometimes they are slightly different. So let's say you've got an initial temperature of 19.2 for your sodium hydroxide. Okay, now the mass of that, or volume, would be 100 mils. Okay, and you're going to use a graduated cylinder to measure that out. And then you're going to take the temperature of your hydrochloric acid, and let's say the temperature of the hydrochloric acid, using the same thermometer but you've cleaned it off, is 20.1, and the volume of that hydrochloric acid is 100 mils. Okay, now you pour the sodium hydroxide and hydrochloric acid together into the calorimeter, and so your initial temperature of your calorimeter is going to be the average of the two temperatures, like 19.2 plus 20.1, and then you divide it by 2, and that will give you 19.7. Okay, now once your reaction has occurred, you should get a final temperature, and these numbers have just kind of like made up. Say I've got a final temperature of 22.5 degrees Celsius. Now the volume that's now in your calorimeter is 200 mils, which is approximately 200 grams. Okay, one of our assumptions for calorimetry is that we're going to treat any solution that's in the calorimeter like water. So it's going to have the same density of water, it'll have the same specific heat capacity, and so on. So the mass of the water in the calorimeter, its volume is 200 mils, and so we will just assume the mass is 200 grams. Okay, now we're trying to determine the heats of reaction for sodium hydroxide, and so the equation we're going to be using will be N delta H for sodium hydroxide, and it's going to equal the MC delta T. Now the MC delta T is for the calorimeter, the solution that's in the calorimeter. Now the fun part in part A is determining the number of moles for sodium hydroxide, because we don't have a mass here, so we can't use mass divided by molar mass. What we're being given in our lab is the concentration, and they tell us that the concentration of our aqueous sodium hydroxide is 0.500 moles per liter. So to calculate the number of moles, we are going to use the formula concentration is equal to the number of moles divided by the volume. Okay, now this type of concentration is also known as molarity, but we just use the capital C so we don't mix up molarity and molar mass. Okay, now to find the number of moles, we need our concentration of the aqueous sodium hydroxide, which was the 0.500 moles per liter. Okay, it's going to equal N for the number of moles divided by the volume of sodium hydroxide we used. And we only used 100 milliliters, which works out to be 0.100 liters. Okay, we've got to convert that milliliters to liters so that our units are the same. Okay, now multiplying both sides by the 0.100 liters, we'll get the number of moles by itself, and we discover we have 0.0500 moles in our aqueous solution. Now from there we can take our equation, the N delta H of sodium hydroxide, it's going to equal MC delta T. We'll divide both sides by N, the number of moles, and that'll give us our enthalpy, change in enthalpy for sodium hydroxide. Okay, it'll equal MC delta T. Now that MC delta T is from the calorimetry. The N that we're dividing it by is the number of moles of sodium hydroxide that we have. Okay, so our delta H of sodium hydroxide will equal 200 grams times specific heat capacity, 4.16, times our change in temperature, which was final temperature 22.5 minus 19.7, and then we divide it by the number of moles, which we just found just above 0.05. Okay, now I'm going to let you calculate that out, and that will give you the heats of reaction for part A. Now, when we do part B, we can make a table that's very similar as what we made in part A. Okay, so, but in part B, now what we're going to be doing is we're going to be adding some sodium hydroxide pellets to some hydrochloric acid. So we're not going to have initial temperature for sodium hydroxide. All we're going to worry about is the mass. And they suggest that you use approximately 1.95 grams of pellets, or one pellet less than 2.05 grams. So anything around the 1.95 grams is fine. Okay, but don't put 1.95 grams down. Mass out your pellets and write down the mass that you obtained when you weighed it. Okay, now the hydrochloric acid, we're going to be using in this case 200 mils. So we take the initial temperature of that, which is 20.1, and it's 200 mils. Now, the solution in our calorimeter is going to be based on the hydrochloric acid, aqueous. So the initial temperature of our calorimeter was 20.1. Okay, we add our pellets to it, and then we take the final temperature, and we discover that it goes up to 26.5. So this guy here is an endothermic reaction. It's going to be absorbing heat from the universe. And again, the mass or volume is 200 mils, which is 200 grams, because again, the solution in our calorimeter, we're going to assume that it takes the properties of water. Formula we use is the same as part A, and delta H, sodium hydroxide, equals MC delta T. Now in part B, since we're using a mass, we can find the number of moles of sodium hydroxide by using the formula N equals M divided by mm, or moles is equal to mass divided by molar mass. Okay, now the mass that I used in my table was 1.95 grams, and then I'm going to divide it by the molar mass of sodium hydroxide. Now to calculate the molar mass of sodium hydroxide, I have one atom of sodium, which has a molar mass of 22.99 grams per mole. I had one atom of oxygen, which had a molar mass of 16.00 grams per mole. And I had one hydrogen atom, which had a molar mass of 1.01 grams per mole. Okay, add those together and do your division. You'll have the number of moles of sodium hydroxide for part B. And I'm going to let you calculate this on your own. Okay, again, we use the formula N delta H of sodium hydroxide equals MC delta T, dividing both sides by N. That'll give us the heats of reaction for sodium hydroxide. Okay, now the mass is the mass of the solution in the calorimeter, which was 200 grams. Specific heat capacity is that of water, 4.16. Change in temperature, well, that's our final minus our initial, so 26.5 minus 20.1. And then we divide it by the number of moles of sodium hydroxide that we just discovered at the top. Okay, now that'll give you your heats of reaction for part B. Now part C is very similar to part B, so we can create a table that's very similar to part B, except instead of using aqueous hydrochloric acid, we're going to substitute it for distilled water. Okay, but we will be using sodium hydroxide pellets and some distilled water. Again, we can't take the temperature of those pellets, so we'll just worry about the mass of them. So again, we'll go and try and mass out 1.95 grams. Okay, we're going to be using 200 milliliters of distilled water, so we take its initial temperature. So let's say this distilled water had a temperature of 21.5. Okay, the volume's 200 mils. So our calorimeter initial temperature is 21.1 degrees Celsius. We add our pellets to the distilled water in the calorimeter, and we take the final temperature once they're all dissolved, and we discover it's 23.8. Okay, and the mass, the solution in our calorimeter is 200 grams. Okay, and again, we're going to use the same equation, number of moles times the delta H of the sodium hydroxide is going to equal MC delta T. And the calculations for part C are the same as part B, so I'm not going to go through these in the next step. Now, what you're supposed to do at the end here is you're going to try and determine and demonstrate a relationship among the three reactions and the three delta H values. So you will have 3 net reactions. Now the lab gives you 2 of those net reactions. They give you a net reaction for part A, and then they also give you the net reaction for part C. What you get to have fun with is determining the net ionic reaction for part B. So if you don't remember how to calculate a net ionic reaction, please watch the video that I posted under the labs on how to determine net ionic reactions. Okay, next slide I'm going to show you is we're going to try and determine a relationship between the heats of reactions for parts A, B, and C. So what you're going to want to do is you're going to take the heat of reaction that you calculated in part A and add it to the heat of reaction you calculated in part B and see if it's approximately the heat of reaction for part C. Now these aren't going to be exact, they might be off a little bit, but again what you'll try and do is you'll take the heat of reaction for part A, add it to the heat of reaction you calculated in part C, and see if it's equivalent to the heat of reaction you found in part B. If it's not, or maybe you might want to try and see if the heat of reaction for part B added to the heat of reaction for part C is equal to the heat of reaction for part A. Okay, try all 3 of those combinations and find out which one of the 3 comes closest. Okay, and then that will be your relationship. Okay, then take a look at your 3 net ionic equations and using Hess's law, add the 2 up and see if you get the third one.